Hello, so this is a video in a series on eigenfunctions of the Fourier transform. This specific video is about orthogonal polynomials related to the Hermite polynomials. And the idea is that, let's just read it. So it says, we approach the construction of polynomials P of X. So we have polynomials times this Gaussian here. We want them to be orthonormal in L2. So remember the inner product for the L2 is that you do integrate f g bar dx. And here the degree of Pn is n. So we want the set of all these to be orthonormal. Earlier in the series, we showed that if you take the space Vn, which is going to be polynomials of degree at most n, times this Gaussian, then these give you n plus 1 dimensional subspaces. And every time you increase n, it gets a bigger subspace. And you can get an orthonormal basis in here of eigenfunctions for the Fourier transform. And this right here is going to be an approach. And we also showed that it was dense in L2. If you just wanted a basis for L2, an orthonormal basis, what you could do is just apply Gram-Schmidt, basically. However, another way to do it is that we're going to talk about in this page is we're going to talk about how you can find an orthonormal basis of polynomials of Pn. And so let's just do that. So another approach we talked about last time was the raising and lowering operators for this operator. We only skimmed it earlier, but we're going to take a different approach. It turns out the different approach is basically going to give us the same result. And however, we'll prove that at the end. So this theorem is called Rodrigues' formula, and this is you can find it on Wikipedia. The version I have here is a simplified version of that. It's just easier to prove, and it's just the thing that's relevant to our example. So trying to decide what I want to do. Yeah, so actually to see our example, the example that we care about is for these Gaussians, these polynomial times of Gaussian. So if we have Pn e to the minus pi x squared, inner product Pm e to the minus pi x squared, that turns out to be integral of Pn, Pm, and then you have to multiply these Gaussians. One of these gets a conjugate. You multiply these Gaussians, you get minus 2 pi x squared dx. So it's orthogonal polynomials up to this weight factor, which is not the Gaussian that we started with. It's a different Gaussian. However, this Gaussian is going to match this theorem here, which is kind of more general. So suppose we have some Schwartz function that's positive, and we're going to satisfy this differential equation here. Now, this example, if you differentiate, then 2x comes down, so you get minus 4 pi x e to the minus 2 pi x squared. So we have minus 4 pi x, so ax plus b, so a is negative 4 pi and b is 0. But in general, this is the equation. And if you were to solve this, it's going to be the integral, c e to the integral of ax plus b dx. So this is going to be a constant, e to the a over 2x squared plus bx. And in order for this to be a Schwartz function, you need a to be negative. So this is, in general, the w that we're going to have. Rodrigues' formula, the one on Wikipedia, is more general. But this is just the simple example that we're going to have. So consider the problem of finding orthogonal polynomials. Pn is 0 if n is not equal to m. For this integral. This is exactly the example that we had earlier. Then you can choose Pn to be this formula here. We take w here, you differentiate n times. And the idea is that every time you differentiate it, you still get multiples of w floating around because of this identity. So if I did the second derivative, then I differentiate this, but there's always a w, and we'll do some examples, but the w's don't go away. And so because you keep differentiating, you get polynomials times w, you need to divide by w to get rid of the w's, so you just get a polynomial. If you want these polynomials Pn and Pm to actually be orthonormal, not just orthogonal, like this integral here being the Dirac delta, the Kronecker delta nm, I have a formula here for what these fn's are. So here's that polynomial Pn. However, there's a factor here, n factorial. There's that leading coefficient made positive to the nth power, and then also the integral of w. But we'll go over that in a little bit. So before we go over our proof, let's do some examples. So remember, Pn is w. I do n derivatives, and then I divide by w. So let's do some examples. So 0th derivative says don't do anything. So just w divided by w is 1. P1 is a single derivative divided by w. First derivative is ax plus b times w. W is canceled, you get ax plus b. Second, you do 2 derivatives divided by w. So first derivative times, you either do another one. If you do the derivative of the ax plus b, you just get aw. You do the derivative of w, you get another ax plus b. Now, when you divide by w, the w's go away. So you get a squared x squared. You get 2axb, that's this, and you get b squared. And then if you write it as a quadratic, it's a squared x squared, 2abx, and then a plus b squared. And you can see every time, if you just keep differentiating w, you always have w's times polynomials. And what do you see here? The proof is going to start here. Pn is a polynomial of degree n with leading coefficient a to the n. So we can see that in the example, leading coefficient is a to the 0, a squared. Well, why is it leading coefficient a to the n? Well, it's kind of by induction, basically. If you had an x to the n plus some lower terms times w, and you were to differentiate this, now if you differentiate the polynomial degree goes down. So it's p prime w plus pw prime. If you do p prime, the degree goes down. If you do pw prime, well, pw prime is p times ax plus b times w, and this increases the degree. So it's p times a higher order. If the leading coefficient of p was a to the n, you're going to get another a, so it's going to be a to the n plus 1. So that's the idea. So p is going to be a polynomial of degree n with leading coefficient a to the n. This shows linear independence. Well, because the first degree is p0 is 1, and then every time you find the next one, it has a higher degree, which means linear independence right off the bat. So consider the example that n is bigger than or equal to m. That's just for simplicity. I guess I should write conjugation here just because. But I guess I have to technically do it. Anyway, so the inner product here, Pn, Pm, W. What do I have? So actually, I guess I don't technically need them because the theorem doesn't say the conjugation. However, these polynomials are going to be real anyway, because a and b are real and everything here is real. So the conjugation doesn't do anything. So conjugation doesn't do anything, so I can just ignore it. The theorem stated doesn't have conjugation in it, so I would be careful about putting conjugation, but it doesn't actually matter. So this right here is just this thing by definition. The w's here will cancel, and so I get this. Now what you can do is do integration by parts m times, and the idea is that there are going to be no boundary terms because w is source function. So the boundary terms always vanish when you do integration by parts in this example. So you move this over, you get -1 to the m from the integration by parts m times, and then derivatives hitting the Pn. Now this is the key thing about the degrees. If n is less than m, then Pn has degree less than the number of times you're differentiating it. So it's going to be 0. So this integral up here will be 0. That gives you orthogonality. If n is equal to m, then this integral here, which is when n is equal to m, is going to be this, which is exactly the thing that we calculated above. These are the steps that we did. Now, what is this? Well, Pn has a leading coefficient a to the n, x to the n, etc., etc. If you differentiate n times, well, what happens is that you keep differentiating, the n's come down, and you just get n factorial times this a to the n. All the other terms will have vanished. So this thing right here is just this. So it's -1 to the n factorial a to the n integral of w dx. So if I want to normalize it, I have this factor here times this polynomial. And I actually need to put a square root here. Oops. There actually needs to be a square root. Just so when you square it, the square root goes away and then you get 1 for the integral. Okay, so this right here, these polynomials will not be not just orthogonal, but they'll also be orthonormal. So that completes the proof. So for us, what do? We choose the polynomials Pn. Sorry, this w that we have, the example that we cared about, was minus 2 pi x squared. So the Pn's that we get are this. You differentiate this Gaussian n times, and then you multiply by that Gaussian 1 over the Gaussian. And you see from this identity that we had, if you differentiate the Gaussian, we get minus 4 pi x. The a is negative 4 pi, and b is 0. So this is the orthogonality when n is not equal to m. When n is equal to m, then I kind of just repeat the calculation, but this inner product here is this, which should be a to n here. So it's this. So this is the integral of w. So what is the integral of w? Negative 2 pi x squared dx. Well, basically, I know that the integral of minus pi x squared dx is 1. So I'm going to do a u substitution, basically. So this is e to the negative pi root 2 times x dx, or sorry, squared, and then root 2 dx, and then 1 over root 2. Now this integral is going to be 1, because I do a u substitution to get this, and then I get 1 over root 2. So this integral becomes 1 over root 2, and then I'm just left with all this stuff. The negative and the negative come together, and I get 4 pi to the n over root 2 n factorial. So this example that I have down here, which is a square root of this thing, just wanted to be clear. So these are the polynomials that I get. I get the Pn's, and then I get multiplied by the square root of this factor. So let's do some examples. Examples are P0 is this exponential factor. I mean, P0 is just 1, so that's the example. P1 is ax plus b, that we already did these calculations earlier. P1 is this times the exponential. That's negative 4 pi x times this. P2 is this ugly thing, but then we have to use the fact that a is negative 4 pi and b is 0. 4 pi, yeah, 4 pi, just 4 pi. So this right here becomes 16 pi squared x squared, b is 0, b is 0, and then minus 4 pi. It's Gaussian. P3 is this example here times the Gaussian differentiating, and then you multiply by the other factor. So if you do this product here, you get this basically. And then if you simplify, you get this. The key idea is that these P0, P1, P2, P3, these are multiples of the Gaussians that we had in our previous example, which is that we calculated the Gaussians here using the raising operator. And they were just multiples of each other. So that leads one to speculate that is always going to be true. Turns out to always be true. These are multiples of the eigenfunctions found using the raising operator. And if we normalize, then we get this ugly thing. And these are eigenfunctions. And the proof of that is that, so first of all, we show that these were here eigenfunctions, the orthonormal basis for L2. However, we didn't show that they're eigenfunctions of f. That kind of seemed like a hard thing to show, except for the fact that it turns out that it's deeply related to the raising operator, which we had earlier. And the raising operator, x plus id times the Gaussian, these were eigenfunctions. We showed that. So if we show that these are eigenfunctions of the Fourier transform coincide with these things, I mean, up to a factor, then this right here becomes an orthonormal basis for L2, and they're eigenfunctions for the Fourier transform. So that's our goal. So we're going to prove that. So we only need to prove the last part. The last part is that these are multiples of the other ones. So let's let w to be e to the negative pi x squared. This is not the same w that we had in the proof for Rodrigues' formula. Note that dw is I over 2 pi derivative of the Gaussian. When you do the derivative, the negative 2 pi x comes down. You get I over 2 pi. So the 2 pi's cancel and you get negative I with an x. So negative ixw. So dw is negative ixw. Note that Fn Fn is you take this Gaussian here, n derivatives, and then multiply by this Gaussian. Now, the question is, why is there a negative 2 pi here and then a pi here? The reason is that the polynomials that we found were you took the negative 2 pi x squared, do the n derivatives, and then you multiply by 2 pi x squared. This is just the polynomial. If I want the function that's actually in L2, I have to then multiply this by the standard Gaussian, which will then take this 2 pi x squared and turn it into a normal pi x squared. So this is the formula. And this formula, so this d to the n is basically this d to the n, except the fact that they have these factors here. So this Fn is just n times differentiating w to the n, w squared, and then you have w inverse. That's basically w squared here, and then w inverse, because w is the inverse of the sign. So this Fn is equal to this up to a constant, non-zero constant. And we want to show that this thing is basically the thing you get essentially from the raising operator. So let's do that. If you just do it deductively, basically. So if you have 0, d to the 0. D to the 0 does nothing by definition. So w inverse w squared is just d to the 0 goes away. So you can just get w. W is the Gaussian. That's the same thing as eigenfunction of the Fourier transform. It's the same thing that you get from the raising operator, but apply to this. Okay, so now let's do n plus 1. So if you do n plus 1 here, you get w inverse w d to the n. Now what I want to do is I want to basically look at this. However, I need to then get the d that's in here and move it out. So basically the idea is a commutator relationship like this. This is kind of, I write this for people who kind of know what this is. Basically, this is the thing that we want, kind of, if we move the d out. However, you have to then deal with the fact that these are in the wrong order. So this is kind of like the error term. So let's just write out explicitly what I mean by that. Oops, I somehow lost the pen. Okay, so you see here that the term that I want is this term all the way to the right here. That is where the d has been moved out, and it's applying to this whole thing. So what I need to do is, because I started with this thing, I need to add and subtract. So I subtract here, and then I add. And this is the thing that I started with here. Now I can then calculate what all these different things are. I'm going to leave this alone. That's just here. This thing, the d, I can use. I'm going to leave this alone too because I like this thing. And I'm going to use the product rule here. So because d is just a multiple of differentiation, I can use the product rule. So if I do minus d w inverse, and then d to the n w squared, and then if I do the product here, I get minus w inverse d applying to this thing. Now, if you look here, this thing and this thing are exactly the same, except with a negative sign. So they cancel. So I'm left with only this and left with this. Now, the idea is that d of w inverse is just like differentiation. That's going to be negative 2 d of w. Because remember, d is just a I over 2 pi times the derivative. Oh, also negative sign, sorry. So that's right here. Negative w inverse. There was a negative sign here, so that's why I have this other negative sign. D to the n w squared. and then the derivative of W. And then here's that term that I liked earlier. Now, what is this? Negative, negative cancel. D of W is minus IXW. That's what we showed up here. Minus IXW is D of W. So where am I? Yeah, minus XW is D of W. These I's cancel, so I get minus W to minus 2. This term remains the same. Now what do I get here? This W inverse times a W. It's just W inverse times a D. There's a minus IX. So minus I time with the operator X. This is D times this thing here. So now what I see here? I see this thing here, and I see this thing here, and then I see minus IX. So this is minus IX plus D times W inverse D to the N W squared. And then what I do is I factor out this minus I get minus I X plus ID. So if I put this I into here, you can check that they cancel and you just get 1. So that's the D. So that's what this is. So what I did is I showed that this thing up here so I have it here. I have the formula here. This right here is the thing that I got from Rodrigues' formula. And this is the Gaussian being raised n times with a factor here. So it shows that this thing right here is the same thing basically as the raising operator thing. And then we showed previously that the raising operator gives me more eigenfunctions for the Fourier transform when I start with an eigenfunction. The Gaussian is an eigenfunction. So start with the eigenfunction, and then I'm raising it to get more eigenfunctions. That means Rodrigues' formula is giving me the same answer basically as the eigenfunctions gotten by the raising operator. However, the nice thing about the Rodrigues' formula is that I can easily normalize it, which I had already done. So it tells me the same answer is gotten by these two different methods. And that's related to what they call the Hermite polynomials. And me not being an expert on it and noting that the convention that I'm using is different than the convention that people were using on the Wikipedia page, I'll direct you to the Wikipedia page for the Hermite polynomials, and you can learn about it there. But that's why I call them HN. So these are, I'm going to get Hermite polynomials times that Gaussian, and these are going to be my functions. However, these are not the same HN that are on the Wikipedia page. So hope you found this series interesting. This is the conclusion. So basically, we found the eigenfunctions for the Fourier transform. We wrote them down in 2 different ways. So one way to write down the eigenfunctions, a dense subspace will be spanned by things like this. However, Rodrigues' formula gives you a nice formula for it that's deeply related to orthogonality of polynomials, which is gotten from a completely different perspective. So I hope you find this interesting, and I hope you have a nice day.